The second derivative, getting it from finite difference approximation, we shall find that it is approximately equal to f of x plus h minus 2f of x plus f of x minus h, whereby x plus h is the same as xi plus 1 and xi minus h is the same as xi minus 1. And h is the step size on the side of x. So this is it. And if given a question, you should be able to use this function and then substituting, then get an approximation to the second derivative of that particular function. Now let us look at the proof. It is not necessary at this level, but it is also important that you understand it. This comes from Taylor series. So Taylor series of f of x plus h. So f of x plus h is equal to f of x plus, like I said, this is the same as divided by 0 factorial, divided by 1 factorial, divided by 1 factorial, then 2 factorial, okay? This is the same as 3 factorial, which is equal to 6, and so on and so forth. Then if it is x minus h, then wherever there is h, you substitute it with a negative h. You just flip where there is positive, you put negative, but then you be careful, because for h squared, it is going to remain a positive, because if you have negative h squared, you remain with a positive. So that's why when it comes to this one, you have f of x minus h, the first derivative of f of x plus h squared out of 2, then second derivative f of x minus h cubed, the third derivative f of x, then divide by 6 or by 3 factorial, then plus the truncation error, and we said this is the O, which is the terms of h to power 4 and higher. So in other words, another person would have put OH to power 3, so you can say the terms of h cubed and higher. But this is giving you what we call the truncation error. The truncation error. So because as you we see that the truncation error is directly proportional to h power 4 here. So that means as you go to higher powers of h, the error keeps on reducing. The error keeps on reducing. That's what we are meaning. So now, if you are to determine the if you wanted the second derivative of the function, you already see it in this. Let me call it equation 1. This is equation 2. So you already see it here, and you already see it here. So it's a matter of like getting this and that. You add them together, you maintain the f prime, because if you got this minus that, you see that second derivative would vanish. So the only way to maintain it is getting this plus that. Okay, this and that will go, but still I have the f double prime, which is the second derivative of the function that I'm interested in. Now, if I add this plus that, obviously I'll have f of x plus h, then plus f of x minus h, okay, equal to 2f of x. Then this and that will go because they are the same but opposite because of this negative sign. So plus 2, okay, 2h squared f second derivative of f of x divided by 2. Then this and that will go, and that and that. Obviously, it will maintain that O, okay, that plus maybe let me say twice of O h to power 4. So this and that will go so that I have f of x plus h plus f of x minus h equal to this and that will go. Let me put this f of x the other side. So minus 2 f of x, okay, equal to h squared f double prime x. If I add this, remember this other value, anyway, let me add it there so that I have the twice or h to power 4, okay. So when I come here, I can divide both sides. I can divide both sides by h squared because I want to make f double prime the subject of the formula. So now I'll see that my f double prime of x, or the second derivative of this function, will equal to f of x plus h plus f of x minus h minus 2 f of x divided by h squared, then minus this value, which will be now O h squared. In other words, I'll have this truncation error in terms of h squared and higher. So if I bring in this, the interpretation of this error, I'll find that since I have the higher terms of h squared, then I'm going to find that this error is very small and I can neglect it. So if I can neglect it, that's why when I reach here, I find, so if I reach here, I can neglect that error, and then I'll find that finally, the central difference for the second derivative is approximately equal to that. And that will be the formula that you're going to be using to calculate for the second derivative of any function when we are talking about numerical differentiation. So let us take an example of a cos of x. So cosine of x at x is equal to pi out of 4 using the finite difference method with h equal to 0.0001. How are we going to do that? Obviously, we are going to use this method. So to compute the cosine of x at x is equal to pi out of 4 using the finite difference method with the step size h is equal to 0.0001, we have to use the central difference method. It's what we are going to use, and we shall be able to determine the second derivative of the function. First of all, we need to know the exact value of f of x, the second derivative of f of x at x is equal to pi out of 4, and we know f of x is cos of x. So if we take the first derivative of x, of f of x, then we will find that we have negative sine of x. The second derivative, we now differentiate this, and this becomes negative cos of x. We get back to this, but now the negative remains there. So if we take cosine of pi out of 4, it is approximately equal to 0.7071. So when we maintain that negative, it becomes negative 0.7071. Now, if we are to use the central difference method for h equal to 0.00001, we are going to get the second derivative of x, okay, of f of x, okay, at x is equal to pi out of 4. And we are going to substitute in. So cos pi out of 4 plus 0.0001 minus 2 times cos of pi out of 4, then plus cos of pi out of 4 minus 0.0001 divided by 0.0001 squared. So the answer that you're going to get when you press on your calculator is going to be negative 0.7071, okay, and 068. So that is according to my calculator. So I can say f of the second derivative of f of x at x is equal to pi out of 4 is approximately equal to negative 0.7071 as required, and this is 4 dp in 4 decimal, using 4 decimal places. And if I use the exact value is equal to negative cos of pi out of 4, and this is also the same as negative 0.7071 to 4 decimal places. So this is how you can use the central difference method or the central difference formula to calculate the second derivative of a function. So please be mindful of how you place these figures on your calculator. Make sure that you place them the way they are, okay? But change your calculator to radians, and then divide by that. You will be able to get a value that is close to this, actually the same as that. And when you compare it with the exact value, you see almost the error is 0. So the central difference method gives a better approximation of, first of all, the first derivative of a function and the second derivative of a function.